Welcome, curious minds, to another deep dive. Ever found yourself staring at a massive system like SAP and just feeling that overwhelm?
Oh, yeah. Trying to figure out how it all works.
Exactly.
Yeah.
So much information, and trying to make sense of it quickly, it's tough.
hmm
Well, that's what we're doing today. We're going deep into something that sounds super technical, maybe a bit, obscure,
Uh-huh.
SAP memory management, but it's actually fundamental to how these systems even breathe.
It really is. And we've got a stack of sources here specifically on SAP-basis memory management, covering role memory, extended memory, and heap memory.
Right.
And like you said, our goal isn't just defining terms. We want to really understand how SAP applications use your computer's RAM.
The physical memory.
Exactly.
Yeah.
And why people call it a sensitive topic.
Right.
Because getting it right or wrong directly impacts performance.
Yeah.
Massively.
So we're connecting the dots today, uncovering maybe some surprising stuff.
That's the plan, giving you that shortcut, that deep understanding of something really critical.
Okay, let's start at the beginning then. Memory. We're talking about RAM, right? The physical memory chips in the machine.
Yep. Random access memory, the computer's workspace, where everything active happens.
And the big question is, how does SAP actually use this workspace? Is it efficient? Or, does it just gobble it all up?
Well, that's the core of memory management, isn't it? How effectively it utilizes that resource. And to get that, we first need to talk about the idea of an instance.
An instance.
Okay.
What exactly is that in, simple terms?
Think of it as the whole package needed to run an application. It's the RAM allocated specifically for it, plus all the background processes that need to fire up.
So memory plus processes equals instance.
Pretty much. The processor starts the processes, RAM gives the memory to live in. That combination, that's the instance, the application's footprint on the system.
Got it. So it's not just the program file, it's the whole running, breathing entity.
Exactly. And managing that footprint is key. Our sources use a pretty good analogy, a layered cake.
Ooh, cake. I like cake. Tell me more.
Okay, imagine one server, one physical machine. Let's say it has 16 gigabytes of RAM.
Okay, 16 gigs. Decent machine.
And you do a central installation, meaning everything's on this one box. Your operating system, your database, and your SAP application.
All sharing that 16 gigs.
Right. So that RAM gets sliced up. First layer,
Yeah.
the operating system. It's a big application itself, right? Starts maybe hundreds of processes just to run the server.
Sure. Windows, Linux, whatever it is.
Yeah. And the source suggests it might take, say, 4 GB of that 16 GB just for itself. We won't dive deep into OS memory today. That's a whole other world.
Great. Scope creep. Keep it SAP basis.
Yeah, exactly. But it's the foundation. It takes its slice first.
Okay. 4 gigs for the OS, layer 1. What's next on the cake? The database.
Yep. The database instance, let's use Oracle as an example. Another big, hungry application.
Databases love memory.
They sure do. So maybe this Oracle instance gets allocated 6 GB in our example.
Okay, so 4 for OS, 6 for Oracle. That's 10 GB gone already.
Right. And Oracle, like the OS, has its own really complex internal memory structure. You hear about the SGA, the system global area.
Vaguely. Buffer cache, shared pool, redo logs, stuff like that.
Exactly. Buffer cache, redo log, buffer shared pool, stream pool, Java pool, large pool, fixed SGA.
Yeah.
All these intricate parts within its allocated 6 GB.
Wow.
And it has its own background processes too. DB writer, log writer, checkpoint, SMON, PMON. Essential stuff for the database to even function.
So the database instance is like its own mini universe running inside that 6 GB slice.
Precisely. Self-contained. Processes and memory working together.
Which leaves us 6 GB remaining from our original 6 GB. Is that for SAP?
That's it. The final layer of our cake. The SAP instance gets the remaining 6 GB in this example. And this is our main focus today, how SAP manages its slice.
Okay.
And just like the OS and the database, SAP has its own vital processes running within that memory.
Like the ones users interact with. Dialog processes.
Exactly. Dialog processes for user interactions. Background processes for, well, background jobs. Update processes for keeping data consistent. Spool for printing.
In-queue for locks, message server, gateway for connections.
You got it. All those core SAP processes, if you actually looked in Task Manager on a Windows server, you'd see them running. Things like disp plus work.exe, smsgserver.exe.
Ah, okay. So those executables are the SAP processes living inside that 6 GB SAP instance memory.
Correct. The combination of that 6 GB memory allocation and all these essential SAP processes, that's the SAT instance. Handling user requests, running jobs, keeping things moving.
That layered cake analogy really helps visualize how everything shares the machine. OS, then database, then SAP, each with its own instance, its own memory, its own processes.
It sets the stage. Now we can zoom in on that SAP instance and see how it manages its own 6GB internally.
Right. So moving past the big picture system view, let's get into the specifics within SAP itself.
Let's do it.
Okay, this is where we hit the classic SAP memory architecture, the foundation. And like you hinted, things have changed, but we need to understand this first, right?
Absolutely. This is the bedrock. So in this classic view, SAP's memory is primarily divided into three main areas.
Three pillars, what are they?
First, you have role memory. Second, extended memory, which you'll also hear called shared memory. Same thing.
Okay, role, extended shared, and third.
Third is heap memory, also known as private memory.
Role, extended shared, heap private. Got it. The three classic areas.
Now, before we track how a process uses these, we need one more concept, the user context.
User context sounds like everything about me when I'm logged in.
Pretty much. Think of it as your digital footprint inside SAP. Everything you do, everything the system does for you from log in to log out, it's all bundled in your user context.
Okay, what makes up this footprint?
Our sources break it down nicely into three parts. First, your initial information.
Like username, password, what I'm allowed to do, authorizations.
Yes, exactly. Username, authorizations, password hash, your address details from your user master record, the basic ID stuff.
Makes sense. Part one, what's two?
Second is the external session. These are the things you actively do. Typing in a T code like ST04 to check the database.
Or ST03 for workload stats.
Right. Or running a specific program, maybe RSTP test. Any direct action you initiate. That's your external session.
Okay, my direct commands. And the third component.
That's the internal session. This is the system working behind the scenes, usually because of your external actions.
So when I run ST04, I just see the screen. But SAP is doing stuff internally.
Loads of stuff. It's calling other ABA programs. It's connecting to the database. It's sending SQL commands like selects from, fetching data, formatting the screen.
Yeah.
You know, all those internal call statements you might see in code.
Right. Call screen, call function.
That's the internal session firing off back on your external request. So the user context is really the combination of all three: your identity, your actions, and the system's internal responses.
And every single user logged in has their own separate user context.
Absolutely. Each person has their own bubble of information and activity being tracked.
Okay, that's crystal clear. User context is the whole package. Now, let's follow a dialogue work process, the kind that handles my screen interactions on its journey through those three classic memory areas: role, extended, and heap. Because you mentioned dialogue and non-dialogue use memory differently.
That's a key distinction, yes. The sequence is different. We'll start with dialogue as it's the most common and probably the most intricate.
All right. Where does it begin? Role memory.
It starts even smaller with something called role first. Every dialogue work process gets its own little private piece of role memory right at the start.
Okay, a little starter piece.
And its size is set by a parameter. It's role first. And here's the kicker, the really surprising part. Its default size is often just 1 byte.
1 byte? Seriously, how can you fit anything in 1 byte? My name wouldn't even fit.
Exactly. Think about your user context, username, authorizations, session info. Way more than 1 byte.
So it's instantly useless. Or not useless, but instantly inadequate.
Inadequate is the perfect word. It can't hold the initial user context. It's like a tiny doorstep. You can't stay there.
So what happens immediately? The system must do something.
It does. This triggers a crucial event called rollout. Because that 1 byte role first area is too small, the system immediately copies the entire user context from that tiny role memory space into the next much larger area, extended memory.
Okay. So rollout, copy context from role first to extended memory. Happens right at login or the start of a dialogue step.
Correct. It's the context literally rolling out into a bigger space.
Well, extended memory, you also called it shared memory. Why shared? That sounds important.
It is. Shared memory is the main place the user context lives after the rollout. Its total size for the whole SAP instance is set by minutial sizem. Could be big, like 2 GB in the example.
2 gigs, that's a lot more than 1 byte.
Definitely. But here's the shared part and a key restriction. Another parameter, role extension AGF, limits how much of that 2 GB one single dialogue work process can use for one step.
So like the whole pool is 2 GB, but one process might only be allowed to use, say, 10 millib of it at a time.
Exactly like that. The source used 10 millib as an example limit per dialogue process. It's a shared pool, but with individual limits.
Okay, and this sharing enables some clever efficiency, right? This is where your coffee break analogy comes in.
It does, yeah.
Huh.
It explains the why behind shared memory perfectly. Imagine a work process is like a taxi driver. It picks you up, the user, for a journey in SAP, say, running a report.
Okay, I'm in the taxi.
Now, halfway through, maybe the system needs input from you, or you pause. You effectively stop for a coffee break. The work process becomes idle, waiting.
Right. What does the taxi driver do? Wait with me.
No way. That's inefficient. Because the memory, extended memory, is shared, the driver, work process, can drop your user context off safely in that shared space. It notes where you are. Then that driver immediately goes off to serve other users who are waiting for a taxi. It doesn't sit idle.
Maximizes resource use. Smart. So I finished my coffee. I'm ready to go. Does the original driver come back?
Probably not. Any other free taxi driver work process can pick you up. And this is where the roll-in happens.
Ah, the counterpart to rollout. How does the new driver know where I left off?
It doesn't need to load your entire user context back from extended memory into its own little role memory. That would be slow. Instead, it just gets the pointer information.
Like the address, the exact location of my context in extended memory.
Precisely. It copies just that tiny pointer back into its role memory. That quick action of copying the pointer, or sometimes the whole context if needed, but usually just the pointer, from extended memory back to role memory. That's roll-in.
So roll-in lets a different work process seamlessly resume my task by just grabbing the pointer.
Exactly. Super efficient. Allows any free process to pick up the work without reloading everything.
That relay race idea is brilliant. Okay, but what if my task, my transaction, needs more than that 10 millib limit allowed in extended memory for that one work process? What happens then?
Good question. If that 10 millib limit in extended memory is breached, the Dialog work process then moves on to use the next memory area, role area memory.
Okay, role area. Another piece of the role memory concept.
Yep. Its total size is set by its role area. Maybe it's 1 GB total for the system. But again, one Dialog process can't just grab the whole gigabyte. There are still restrictions on how much an individual process can consume here too.
So it's another shared-ish space, but a secondary one, used only if extended memory isn't enough for a particular step.
Correct. It's the next overflow area.
And if that's still not enough, if my transaction is really memory hungry, then we hit the last resort.
Then we hit the last resort, heap memory, also called private memory.
Private. That sounds different from shared, extended, and role area. Why private? What makes it dangerous?
It's fundamentally different. When a work process moves into heap memory, it cannot share its user context anymore. It's completely isolated.
So no more coffee breaks. No more handing off to another work process.
None. That specific work process is now locked to that task. It must finish the job itself, however long it takes, using its allocated private heap memory. It cannot release the context until it's done.
That's why it's the danger zone, because if something goes wrong there, that process is stuck.
Exactly. And our source highlighted 3 possible outcomes once a Dialog process goes into private heap mode.
Okay, what are they?
1. The best case, relatively speaking. The work process completes the transaction successfully, using the private memory it needed.
Phew. Okay, what's 2?
2. It goes into a loop. The program logic is flawed, maybe, and it just keeps running and consuming heap memory without end, potentially stalling things. Problematic.
Very problematic. And the 3rd? Worst case.
3. The program terminates, it hits a limit within heap, or an error occurs it can't handle, and boom, transaction canceled. Error message for the user. Data might be inconsistent.
Ouch. Okay, so seeing a Dialog process enter heap memory is a serious warning sign. High risk of loops or termination.
Definitely a danger sign, as the source puts it. It means the transaction couldn't live within the normal shared memory limits, which often points to an inefficient program or an unusually large data volume for that step.
And this is where tuning heap parameters becomes critical to maybe mitigate those risks.
Yes. There's a total heap size for the instance, ABAP area total, maybe 2 GB again in our example, but there are also limits on how much one Dialog process can use, Dialog heap size, and how much one non-Dialog process can use, non-Dialog heap size.
Right.
And SAP has a strong recommendation here. They say set all 3 parameters to the same value. So ABAP area total, Dialog heap size, non-Dialog heap size, 2 GB or whatever your total is.
Wait, so you don't split the total heap. You let Dialog and non-Dialog potentially use the full amount if needed. Why?
It seems counterintuitive, like they might steal from each other, but it's actually a safety measure. It increases the chance that a process completes if it's forced into heap.
How so?
Imagine the total heap is 2 GB, but Dialog heap size is only 1 GB. If a Dialog process needs 1.2 GB in private mode, it will terminate when it hits that 1 GB limit, even though there's more memory available in the total heap pool.
because its individual limit was reached.
Exactly. But if Dialog heap size is also set to 2 GB, that process can use up to the full 2 GB if available, greatly increasing its chance of finishing successfully instead of crashing. It's about removing artificial internal limits within the private space.
That's a really crucial tuning tip. Give the process the best chance to survive if it ends up in the danger zone. Okay, this whole sequence, roll first, extended roll area, heap. It's complex. We need that food analogy now.
Right, let's plate it up.
Roll first is your starters, that amuse-bouche, one bite, barely a taste, not filling at all.
Definitely not. You need more.
So you move to extended memory. That's the main course, a big shared platter like the 2 GB. But you personally only get a certain portion size at a time, like that 10 milliliter limit.
A good helping, but potentially limited.
And if you're still hungry after the main course...
Then comes roll area. That's
Yeah.
dessert. Another plate, maybe smaller, to top you up if needed. Again, with limits.
Starters, main, dessert. But if, even after all that, you're still not satisfied, the transaction needs more.
There's only one place left. You storm into the kitchen.
Which is heap memory, the private zone. And once you're in the kitchen, 3 things can happen.
1, you finally get enough food and finish your meal. Transaction completes.
Get 2.
2, you eat something dodgy, get an upset stomach, and maybe get stuck in the bathroom. Process loops.
Bad. And 3.
3, you cause too much trouble, and the chef kicks you out. Program terminates.
Worse. Okay, that analogy really nails the escalating seriousness and the finality of hitting heap memory.
Right.
Starters, main, dessert, kitchen. Perfect.
It maps really well to the classic dialogue work process memory flow. Understanding that flow is key.
Absolutely. Now, we've nailed the dialogue process journey. But you mentioned non-dialogue work processes, background jobs, updates, spool behave differently. Remind us quickly of the 2 key differences.
Sure. First, they generally don't have a strict runtime limit like dialogue processes often do. They can run for hours if needed.
Okay, no time limit. And second,
their memory usage sequence is different, strategically different.
Right, so what is their sequence? Not roll first, extended roll area, heap?
No. For a non-dialogue work process, the typical sequence is first, extended memory, then they jump straight to heap memory. And only after that, if absolutely necessary, they might use roll area.
Whoa, okay, so extended, then heap, then roll area as a last resort. That's almost the reverse of dialogue at the end. Why the difference?
It's all about load balancing and using the right tool for the job. Dialogue processes are short, interactive, lots of them. They benefit most from the quick handoffs in shared extended memory.
Makes sense.
Non-dialogue processes are often long-running, heavy-duty batch tasks. They might need large amounts of dedicated memory for extended periods. Heap memory, the private space, is actually better suited for that kind of sustained, heavy lifting.
So dialogue primarily targets extended, non-dialogue primarily targets heap.
Exactly. By having these different primary targets, SAP ensures that both extended memory and heap memory are effectively utilized across the system. You don't have extended memory constantly overloaded while heap sits empty, or vice versa.
It spreads the load, prevents one area becoming a bottleneck for the whole system.
Precisely. It leads to better overall throughput, stability, and performance by using the different memory characteristics intelligently for different types of work.
So again, it comes back to tuning. Making sure extended memory is well-sized for all the dialogue work. Initial size roll extension, and heap is ready for the non-dialogue work. ABAP Memory non-dialogue heap size is crucial.
Crucial doesn't even cover it. Honestly, if you master SAP memory management, understand these flows, know how to monitor, know how to tune, you're incredibly valuable. Our sources literally suggest this skill alone is worth a top-tier salary package for a basis consultant.
Wow. That really underscores the practical importance. It's not just academic, it directly impacts system health and business operations.
Absolutely. Get memory wrong and the whole system suffers. Get it right and things fly.
Okay, so this is clearly a superpower for basis folks. How do they wield this power? Where do they go to monitor and tune all this? Is there like a memory command center?
There is. The primary T code, the one every basis consultant lives in for this, is ST02.
ST02, got it. The memory cockpit.
Exactly. It gives you the overview of buffer performance and memory area usage.
So when you fire up ST02, what are the first things you look at? The vital signs of memory health.
You'll see a few key sections. Right near the top are the buffers and their hit ratios.
Hit ratio, that
Yeah.
sounds like how often it finds what it needs in the fast memory.
Perfect. You want the system finding data in the fast buffer memory, not going back to the slower database or disk all the time. So a high hit ratio is good.
How high? What's the target?
The general rule of thumb is, for most buffers, the hit ratio should be over 90%. ideally 95% or higher. You'll see buffers listed like program buffer, table buffers, export-import buffer.
So C below 90% and it's panic time.
Hold on. Not always. There are a few critical exceptions where lower hit ratios are often perfectly normal.
Ah, okay. Good to know. Which ones?
Specifically, the program buffer, the single record buffer, which is often called initial record buffer now, and the export-import buffer. For these three, it's acceptable, even common, to see hit ratios below 90%. So don't raise the alarm just because the program buffer is at, say, 85%.
Okay, crucial exceptions noted. Program single initial record export-import buffers can be lower than 90%. What about swaps? That always sounds bad in a memory context.
It usually is. Swaps mean the system is running out of buffer space and has to push things out, swap them out, to make room, often involving slower disk access. Generally, you want to see 0 swaps.
0. Okay. Any exceptions there?
One small one. For the program buffer only, SAP considers up to 10,000 swaps per day to be acceptable.
10,000? That seems like a lot.
It does, but programs get loaded and unloaded frequently. The real trouble is if you have low hit ratios and high swaps, over 10K a day for program, or any swaps for others. That combination means the buffer is too small or inefficient. You're definitely in trouble then, as the source says.
Got it. Monitor hit ratios, know the exception. Monitor swaps, aim for 0, except maybe program buffer. What else does STU2 show about the core memory areas we discussed? Role, extended, heap.
It shows their utilization. You'll see sections for role area, extended memory, heap memory, and also paging area, which relates to virtual memory on disk. For each, it shows the configured size in memory and the amount currently being used, current utilization.
And what's the healthy sign here? Low utilization.
Ideally, yes. You want in-memory to be significantly higher than current utilization. If utilization starts creeping up towards, say, 80% or 90% of the available size, especially for extended memory, you're getting close to the limit and might need to increase the configured size.
And what about heap memory utilization specifically, since it's the danger zone?
You really want to see minimal or 0 utilization for heap memory by Dialog processes in ST02. Any significant current utilization here is that danger sign we talked about. It means processes are going into private mode. That warrants immediate investigation into why.
Okay, so ST02 gives you the dashboard, hit ratios, swaps, memory area utilization. How do you actually change things if you see a problem? Like if extended memory is constantly full?
You can often see the relevant parameters directly in ST02, and you can change them using other T-codes. RZ11 for dynamic parameters, or RZ10 for static parameters that require a system restart.
Dynamic versus static, what's the difference?
Dynamic parameters can be changed on the fly, and the change takes effect immediately without restarting SAP. In RZ11 or sometimes ST02, they might have a little check mark or a change value button enabled.
Convenient.
Very. Static parameters, on the other hand, require you to change them in the profile file using RZ10, and then you must restart the SAP instance for the change to take effect.
Okay, so dynamic instant change, static restart required. And which parameters are we typically looking at tuning based on ST02 findings, especially in that classic architecture?
Well, you've got zroll first. Default is 1 byte. SAP sometimes recommended changing it to 124 bytes, 1 KB, to resolve certain niche memory issues, though rollout happens anyway.
Okay.
Then there's role area for the role area size,
Right.
M initial size for the total extended memory size. That's a big one.
Definitely.
And the heap parameters, a boundary period total for the overall heap size, and then dialog heap size and non-dialog heap size for the individual process limits within heap. And maybe page memory size related to the paging file virtual memory. Those are the main levers in the classic model.
Okay. We have gone deep into the classic architecture, the memory areas, the process flow, the monitoring in ST02, the tuning. But now for the plot twist. You mentioned earlier that things have evolved, and this is the part that apparently catches a lot of people out.
It really does. There's been a significant evolution in how SAP manages memory, and it's surprising how many people aren't fully aware of the shift, or still primarily think in terms of that classic model we just detailed.
So what's the big change?
It's a concept called Zero Administration Memory Management, or ZAM.
Zero administration. That sounds nice. Less work for basis.
That was definitely part of the goal. See, back in the day with the classic model, basis consultants had to manually configure all those parameters during installation and tuning. Zroll first, zroll area, M initial size them in, the heap ones. You had to calculate and set them all individually.
Which sounds prone to errors or misconfiguration.
It absolutely was. Get one wrong and performance could tank. ZAM simplifies this dramatically.
What do you configure now?
Now, with ZAM, during the SAP installation, you typically only provide one main parameter related to memory. Physical memory size. This just tells SAP how much memory the instance should use overall on that server.
Just the total amount.
Pretty much. XAMPP then takes that total amount and automatically calculates and configures all the internal memory areas, extended memory, heap memory, buffers behind the scenes. It uses internal heuristics and formulas based on the total memory available.
So no more manual setting of M initial sizem or a Bathia peria total. XAMPP handles it?
Correct. It automates that initial sizing, removing a lot of the complexity and potential for error in basic configuration, makes deployments, especially in cloud environments, much smoother.
Wow, that is a big shift in administration. But what about the underlying structure? Did XAMPP change the memory areas themselves?
Yes, and this is the absolutely key takeaway from the evolution. Under XAMPP and in modern SAP architectures, the entire role memory concept is obsolete.
Wait, obsolete, like role first and role area? They're just gone.
Gone, kaput. No longer part of the core memory management flow in new systems.
Holy cow. So all that stuff we learned about role first being 1 byte and role area being the dessert, that's history now.
It's history in terms of current systems, yes, but it's crucial history to know because many systems might still run older versions, and likely said interviewers might ask about it to test your depth of knowledge. If you only know the new XAMPP way, you might miss questions about role memory.
That's a fantastic point. You need to know the legacy and the current state. So if role memory is gone, what are the main memory areas now? Just extended and heap?
Essentially, yes. For work process execution, you're primarily dealing with extended memory, shared memory, and heap memory, private memory. That's it. Much simpler.
Okay, simpler structure.
Yeah.
Two main areas. How does that change the memory allocation sequences for dialogue and non-dialogue processes? They must be different without role area in the middle.
They are, and much more straightforward. For a dialogue work process in the new XAMPP architecture, it uses extended memory first. If that's not enough, it goes directly to private memory, heap memory.
Straight from extended to heap, no intermediate stop.
No intermediate stop. Expanded heap. That's the dialogue flow now.
Okay. And for non-dialogue work processes, background jobs and such?
Their sequence is now first private memory, heap memory, then extended memory.
So they prioritize heap even more explicitly now, hitting it first.
Yes. It reinforces heap as the primary workspace for those potentially long-running, resource-intensive background tasks. Extended memory is secondary for them.
That really streamlines the flows. Dialogue, extended then heap, non-dialogue, heap then extended, much cleaner.
Definitely cleaner and reflects the removal of the role layer.
And how does STO2, the monitoring cockpit, look different in these newer systems, say NetWeaver 7.4 or S4 HANA? Does it visually show this change?
Absolutely. The STO2 screen itself reflects the new reality. You'll notice a few things.
Like what?
Well, for one, that single record buffer we mentioned often gets renamed to initial record buffers. Minor naming change reflects some internal tweaks.
Okay.
But the big one, the entire section labeled role memory or role area is completely gone from the memory area display. It just isn't there anymore. Yeah.
Wow. Just vanished.
Vanished. You'll only see extended memory, heap memory, and paging memory listed as the main components being monitored.
And what about the parameters list you can see via ST02 or RZ11, RZ10? Are the role parameters gone there too?
Yep. You won't find role first or role area listed as configurable parameters anymore because the system doesn't use them. You only see the parameters relevant to the current architecture. M initial sizem, though often auto-sized by XAMPP. The heap parameters, a BAFI period total, dialog heap size, non-dialog heap size, and the paging parameter. The parameter landscape directly mirrors the architectural change.
That makes perfect sense. The tools reflect the underlying reality, so understanding both architectures, the classic role extended heap flow, and the modern XAMPP extended heap flow is absolutely essential for anyone working seriously with SAP systems today.
Couldn't agree more. You need the historical context and the current state. Interviewers might probe the old way, while day-to-day work on modern systems uses the new way. Knowing the evolution is key to being truly proficient.
What a fascinating journey through the layers of SAP memory. We started way out with the concept of an instance OS, database, SAP, all taking their slices of RAM.
And then we dove deep into that classic SAP memory model, that intricate dance of a dialogue work process through role first, then extended memory, maybe role area.
And finally landing in that critical private heap memory, we saw how non-dialogue processes take a different path, prioritizing heap for their heavy lifting.
Right, and the importance of that private mode. Hitting heap is that danger sign, risking loops or termination. making monitoring via STO2 so vital.
Checking those hit ratios, watching for swaps, keeping an eye on extended memory utilization, and really hoping not to see much heap usage for dialog tasks.
Exactly. But then came the big reveal, the evolution to Zero Administration Memory Management, ZAM.
Yeah, simplifying the admin work, but more profoundly, making the entire role memory concept obsolete in modern systems.
Leaving us with a cleaner flow, extended then Heap for dialogue, and Heap that extended for non-dialogue, a fundamental shift.
Which brings us to our final thought for you, our listener. ZAMM automates a lot of the configuration, makes the administration simpler, gets rid of role memory complexity. But does that simplification actually make understanding the principles of memory use more important?
That's a great question. If you're not manually setting every parameter, maybe the focus shifts.
Right. When things go wrong, when you hit performance issues, even with ZAM, you can't just tweak roll rare anymore. You need to understand why a process might be consuming excessive expended memory or why it's being forced into heap. Even if ZAM set the initial sizes, does simpler admin demand deeper diagnostics?
It's an interesting thought. Maybe the skill shifts from pure configuration know-how to more profound troubleshooting and understanding the behavior within the automatically managed boundaries. Less knob turning, more detective work.
Exactly. Something for you to ponder. So keep diving deep. If you have access, explore ST02. Look at your own system's memory stats. See if you can spot the signs of the old or new architecture.
Keep asking why. That's how you really learn.
Absolutely. Our mission here is always to give you those shortcuts to being well-informed to help you find those aha moments in complex topics. Thanks for joining us on the Deep Dive.
Until next time.